Last week we saw how the electron configuration of certain elements will make them more reactive than others. In particular, we talked about sodium and chlorine. Now, sodium will readily give up one of its electrons to get to the more stable electron configuration that we say is isoelectronic with the noble gas neon. So even though sodium only has 10 electrons remaining, it still has 11 protons in its nucleus. On the neutral atom, the number of electrons and protons will balance. Now, with the unbalanced number of electrons and protons, the sodium atom is left with a positive charge. And a positively charged or negatively charged atom we call an ion. In this case, because it does hold a positive charge, we call it a cation. On the other side of the periodic table, chlorine takes an extra electron to become isoelectronic with argon. Similarly, its electron configuration is now more stable, but it has 18 negatively charged electrons for its 17 positively charged protons, giving it an overall charge of -1. As a negatively charged ion, we call this a chloride anion. If we wanted to keep thinking about atoms in isolation, then we could look at the difference between neutral atoms and charged ions in terms of atomic radius, or ionization energy, or electron affinity, or we could even look at the oxidation states of the transition metals. But instead, let's start talking about what happens when we put atoms close together and start forming chemical bonds. As I'm sure you all know, electrostatically charged objects will attract opposite charges and repel the like charge. So when we place our sodium cation and chloride anion in proximity to each other, their charges attract, pulling the ions close together. And they'll keep doing that until the electrostatic attraction is balanced out against the electron-electron repulsion. Because remember, these are still surrounded by electron clouds. And at this point, the distance between them stabilizes, and it would now take some energy to separate them again. This is called an ionic bond. For our first example, let's look at barium and bromine. Okay, barium, first let's find it on the periodic table. So it's a group 2 metal. It's down here. Alright, so if we think about how many electrons it's going to have in its valence shell, it's going to have a completed set of core electrons up through xenon, and then +1, 2. So its Lewis dot structure for barium is going to look like barium +1, 2 dots around it for its valence electrons. Okay, bromine is a halide, so it's in group 7. And there it is. So its next nearest shell is actually going to be krypton, and it's going to want to move up. So when we draw its structure, or its Lewis dot diagram, we've got 1, 2, 3, 4, 5, 6, 7 dots around it to show its 7 valence electrons. Okay, and so for these two to get to their nearest ionic stable state, that means that for barium, we're going to have to get rid of 2 electrons, and for bromine, we're going to have to add another one. So its ionic form is going to be a barium 2+ cation and a bromide anion. And to combine these into a neutral salt, we need to balance the positive and the negative charge. So every barium ion needs 2 bromide ions. And our final formula for barium bromide is Ba Br2. And we can draw that out as barium 2+ and 2 bromine with our dots negative. So now we're going to run through 2 more examples, and to get the most out of your time, what I suggest you do is to pause the video as soon as you see the example pair come up on screen. Locate each element on the periodic table to determine the number of valence electrons that it's going to transfer when it forms the ionic pair. write out each of the ions with their charges, and then finally balance the two charges to arrive at the neutral salt. Okay, the next two atoms we're going to try is oxygen and lithium. So like I said, at this point, just hit pause on the video and try to build a salt out of these yourself. If you want to check your answer, now we'll go through each of the steps. So first thing we're going to do is find oxygen on the periodic table. So it's right up here in the 6th group. So that means around oxygen, we're going to draw 1, 2, 3, 4, 5, 6 valence electrons. And for lithium, we know that that's a group 1 metal. And there it is. So we're going to draw lithium with just 1 valence electron. That means for these two to get to their nearest stable ionic state, oxygen's going to want to pick up 2 electrons to get towards the neon electron configuration. So that'll be oxygen with now a full shell of 8 electrons around it and a 2- charge. And lithium is going to drop its 1 electron to drop back to be isoelectronic with helium. And so that will look like lithium plus. Okay, and this is a fairly familiar situation, a little bit similar to the barium bromide that we just saw, except now our charges are reversed. So to get to a neutral salt, we're still going to have to balance the electronic charges, and that means that we're going to take 2 lithium for every 1 oxygen. And we can write that out as lithium 2O, lithium oxide. Okay, our last example is going to be a little bit more challenging. We're going to look at gallium and sulfur. Challenging because of deciding how many valence electrons gallium is going to lose. So go ahead and try it for yourself. Okay, and now to verify your answer, we're going to start again by finding gallium and sulfur on the periodic table and talking about what valence electrons are going to drop to get to the next nearest stable ionic state. So we'll start off with gallium, and if you're looking for gallium, it's going to be in the P block, right below aluminum. So that means that if we were going to write out its electron configuration, which maybe is a helpful place to start, we start with argon, and then we have 4s2, 3d10, and 4p1. So if we were going to take gallium all the way back to be isoelectronic with argon, that means that we would have to get rid of 13 electrons, or have gallium 13 plus, which is not an oxidation state or an ionic state that we're going to find for gallium. To really have a look at what might happen instead, let's draw out these electron shells as they would be moving out from the nucleus. So we'll just draw a little gallium in the center to represent the nucleus, and then we're going to draw each of the shells growing outward from that nucleus. So there's 1, 2, 3, and 4. Okay, remember, even though the electrons aren't orbiting like planets, the shells, according to the principal quantum number, really do grow out in diameter. So in our first shell, the only orbital we're going to have there is the 1s orbital. In the second shell now we have 2s and 2p. In the third shell we have 3s, 3p, and 3d. So even though it's not included in the argon electron configuration, that 3d orbital is still the same size as the other 3 orbitals. And then finally, out in the fourth shell, we have 4s and 4p orbitals for gallium. We would also find 4d and 4f at this radius, but of course they're not included in gallium. So if we start to knock off electrons to ionize this gallium, since this is our metal, it's going to lose electrons. Where we're going to start is the highest energy ones. So if we start to take away electrons, the first thing we're going to start with is this 4p. So we'll knock it off. And then we have to decide if we're going to start, so let's get rid of 4p. We have to start with the 3d10 or the 4s2. Now looking at it a little bit more intuitively, if we're going in from the outside towards the nucleus of this gallium atom, we're going to run into these 4s electrons first. Those are the farthest away, and really they're going to be at the highest energy state. So instead of trying to attack this complete 3 shell, including the complete set of 3D electrons, what we're going to do is remove those 4s electrons completely and knock it down to this completed third shell. So what we end up with in terms of gallium is removing these 4s2 electrons, and we have it as an argon core plus the 3d10 electrons, and that's going to be our gallium ion. So we've only removed 3 electrons, so this is going to be a gallium 3+. And we don't have to draw on the other 10 electrons around its valence because really they're not going to be taking part in any kind of chemistry here. Okay, so let's move on to the sulfur, which is a little bit easier. It's directly below oxygen on the periodic table, so it's going to have the same electron configuration as we've already seen for oxygen. So that means we're going to have a sulfur with its 6 electrons, as we would have had for oxygen, and now we're going to add 2 more to make it sulfur 2 negative. Okay, and as always, we want to make a neutral salt out of these two. We can't just pair them up as we would sodium chloride, and there's not going to be an easy one there, but what to do to balance the charges? Easiest thing you can do is just multiply the one by the other to get a common multiple. So in this case, we're going to have 2 gallium 3+, and 3 sulfur 2-, or gallium 3, sulfur 2, gallium sulfide. And that would be our final answer.